In this video, we're going to be looking at how Euler found the sum of the reciprocals of the squares. And in the process, he came upon several important mathematical ideas. One of them is looking at special values of what's now called the Riemann zeta function, which is where you take the same sum but with s powers instead of squares. So Euler found a formula for these values when s is a positive even integer. So the first one was the sum of the reciprocals of the squares, which he found to be pi squared over 6. And then the sum of the fourth powers he found was pi to the fourth over 90. And the sum of the reciprocals of the sixth powers is pi to the sixth over 945. And he actually gave a formula for all of them. Now, I write ... but the pattern is not clear, certainly. And it's pretty complicated, and it's not exactly something that you can compute very easily if the input is large, but it's related to something called Bernoulli numbers. Now, returning to the original problem of how to compute the sum of the reciprocals of the squares, one of Euler's other big ideas that he came up with along the way was to factor functions that you don't usually think of as being factored, like the sine function. So if you start with a polynomial, you can factor it with one linear factor for each of the roots. So Euler said, okay, let's try doing the same sort of thing with the sine function. So the sine function has a root at every multiple of pi. So it definitely has a factor of x, well, assuming this is allowed. And then, well, you might try something like x minus pi, x minus 2 pi, and so on for all the positive multiples, and x plus pi, x plus 2 pi, and so on for all the negative multiples. But there are a few problems with this. For one thing, if you think about what the linear coefficient would be, it would be minus pi times minus 2 pi, and so on, and then you have a plus pi plus 2 pi, and so on. So that's definitely not something that makes sense. So one way to fix this is just to divide out by those factors. Okay, so that's a first attempt. But what you could do instead is x over pi minus 1 for that factor, and x over 2 pi minus 1, and so on, and then x over pi plus 1, and so on. Now this still has a problem, which is that the linear term would be a product of a bunch of minus 1s, infinitely many of them, and that doesn't make sense either. Okay, so we can patch this up a little bit more by writing it in this form: x times 1 minus x over pi times 1 minus x over 2 pi, and then similarly for the negative roots. Now, this doesn't make sense as written, it still won't converge, but there's one last trick, which is to pair each root with its negative, and then it will converge. So, the final formula is that sine x equals x times, now we have a difference of squares, 1 minus x squared over pi squared, 1 minus x squared over 4 pi squared, 1 minus x squared over 9 pi squared, and so on. Okay, now Euler wrote this down without proving it, and it is true, but in some sense he got very, very lucky, because there are many other functions with the exact same zeros, but that are not the sine function. So you can multiply this by lots of different things. One thing you could do, for example, is multiply by e to the x. That doesn't have any zeros, so it won't affect the zeros at all. And just do the same thing. So it isn't so clear that this is really the formula we need to get sine x, but it is correct. Now there's one other detail, which is that there might be a constant out front, but if we use the fact that sine x is approximately x for small values of x, we see that c has to be 1 because all the other factors are essentially 1. Okay, so if we take this formula as a given, then we can solve the original problem of finding the sum of the reciprocals of the squares. So Euler's last trick was to expand out the right side. So there's an x term all by itself, and then to get an x cubed term, we take 1x squared, for example, here, or 1x squared here, or 1x squared here, and all the rest will be 1s. Okay, so we'll end up with plus x cubed, with 1x coming from the x out front, and then minus 1 over pi squared, minus 1 over 4 pi squared, minus 1 over 9 pi squared, and so on. And the series keeps going, of course. Now, on the other hand, we know that sine x has a Taylor series, which is x minus x cubed over 6, and so on, where it's alternating odd numbers with factorials in the denominators. So if we look at the x cubed terms, on the right side we have essentially the sum we want, but multiplied by a minus 1 over pi squared. And on the left we have negative 1/6. So if we look at 1 plus 1 over 4 plus 1 over 9, and so on, we end up with pi squared over 6. And this was Euler's proof. It's not very rigorous, but it does work out in the end. Now we could look at the later terms in these power series and get other identities. It ends up being a bit tricky, though, to get the 4th powers and 6th powers and so on, because you end up having lots of different multiplications to keep track of, and it's a bit of a mess. So there's a better way, which is to go back to the formula, and take logarithms. Okay, maybe it isn't clear how this is going to help, but just go with it for a moment. So we get a sum, for one thing, rather than a product. Okay, now differentiate both sides. And again, this is assuming we can actually do this, but don't worry too much about that. The derivative of log sine is cotangent, and then on the other side we get 1 over x plus the sum of, well, we have 1 over 1 minus x squared over n squared pi squared, and then multiplied by the derivative of that, which is negative 2x over n squared pi squared. Okay, so that's a bit of a mess, but it simplifies pretty nicely. So we can multiply the top and bottom by n squared pi squared and also flip the signs. So we end up with 2x over x squared minus n squared pi squared. And an easy way to remember this is that it's the sum over all n of 1 over x minus n times pi. Okay, so this is a similar sort of thing to the sine product. We have a function with asymptotes at every multiple of pi, and the cotangent is one such function. And the simplest possible function you could make, pretty much, that has that property is the sum of 1 over x minus n pi. Now, it isn't so clear that those two functions really are equal, but luckily they are. And you can justify this with some complex analysis, which I won't get into. And one other thing is we have to be a bit careful with this sum because it doesn't converge absolutely, so it's safest to pair up opposite terms so that we do get some better convergence. Okay, now if we write this out as a power series, well, technically a Laurent series because we have a 1 over x. I won't say what that Laurent series is because it's pretty complicated, but Euler knew what it was. And on the right side, we have, now I'm unsimplifying it, on the right side we have a fraction that can be written as a geometric series. So if we pull out the -2, we get x over n squared pi squared plus x cubed over n to the 4th pi to the 4th plus x to the 5th over n to the 6th pi to the 6th, and so on. Okay, so the coefficient of x is 1 over pi squared times the sum of the reciprocals of the squares. And then similarly for the coefficient of x cubed, you basically get zeta of 4 over pi to the 4th, and so on. So the power series for cotangent is 1 over x minus twice the sum of zeta of 2n over pi to the 2n times x to the 2n minus 1. Okay, so if you can write cotangent x in another way, you can find these coefficients, and that's what Euler did to get his formula. Now it doesn't stop there. For example, if we go back to this product, and we plug in pi over 2, on the left side we get 1, and on the right side we get pi over 2 times the product of 1 minus 1 over 4n squared. Okay, and this turns into something that's called the Wallace product, which you may have seen before. So this part you can write as, well, it's the product of 4n squared minus 1 over 4n squared, and then the numerator is a difference of squares, so it's 2n plus 1, 2n minus 1, all over 2n times 2n. So what you end up with is pi over 2 equals 2 over 1 times 2 over 3 times 4 over 3 times 4 over 5, and so on. So in the numerators you have each even number twice, and in the denominators you have each odd number twice, other than 1. And this is called the Wallace product. It was found by someone named Wallace. He found it actually quite some time before Euler did this trick with the sine function. Wallace found this in a much more roundabout way, using integrals of square roots and things like that. But this gives a more direct proof, assuming you're willing to take the sine product as valid. Now for one last example of what you can do with this product, if we divide both sides by x, we get sine x over x equals this product. Now if we let x be pi I, on the left side, we get the product of 1 plus 1 over n squared, so it's changed the sign. And on the right side, well, how do you plug in pi I for sine? It's not so clear, but what you can do is write sine x as e to the ix minus e to the minus ix over 2I. And now if we plug in pi I, we get e to the minus pi minus e to the pi all over 2I, and then divide by x for another pi I. Okay, what is that mess? Well, we can combine the two denominators to get a negative 2 pi, and then use that to flip the sign. So we get e to the pi minus e to the minus pi all over 2 pi. So we end up with this pretty bizarre looking identity.